So today we are going to discuss the how to delete nodes in AVL tree. So AVL tree already you have seen how to insert nodes and how rotations are happening, left rotation, right rotations, left right rotations and right left rotations. Okay. So similarly we will see here how to delete the nodes in AVL tree. So AVL tree deletion of nodes in AVL tree will be quite similar like deletion of nodes in binary search tree. Only thing is that after deletion we have to look after the balancing factor or the balance factor of that particular node, whether the balance factor is maintained or not, or if it is unbalanced, then you have to rebalance it by rotations. That is the only fundamental difference between binary search tree node deletions and AVL tree node deletions. So here one example you have taken. In this example, these are the four numbers 18, 16, 20 and 35. Based on this binary search tree, we are going to delete each node, and we are going to see how the balancing factor is disturbed and how you have to rebalance it. So first node that we are going to delete is 18. So 18 means this is a leaf node. So leaf node deletion is not an issue. You can simply delete it. So if it is a leaf node, that means one child, then it is not a problem. You just simply delete it. Okay. So only one child. Leaf node means it is only one child. So one child deletion is not an issue. We can immediately delete it. So this is you delete nothing. So first of all, you have to see all the, before deletion you have to see all the balance factor is maintained or not. So in this case, you see in this node what is the balance factor? 1. Node 30 balance factor is 1, 2, 3. Right subtree height is 3, left subtree height is 1, 2, 3. So 3 minus 3, 0. So this is 0. This is also, this node 20 balance factor is 1, 2, 2 minus 2, 0. This also is 0. Okay, similarly this node balance factor is 0 minus 1, which is 1. This node 16 balance factor is 1 initially. Before deleting this node 18 balance factor is 0. Before deletion this balance factor is also 0. This balance factor is also 0. So all balance factor is perfect, no problem at all. Now we are asking that to delete this 18. So if you delete 18 from here, then just that one single child will be deleted, so not an issue. You can simply delete it. Okay, so child deletion, left leaf is a leaf node. So leaf node deletion is not at all a problem. We are deleting first 18. So once you delete 18, then it will be having this resulting binary AVL tree. In this node also, in this tree also, this balancing factor here is 1 minus 0, 1. Balancing factor is 1, 2. In this side also 1, 2. So 2 minus 2, 0. And remaining this left subtree totally intact. There is no need of checking again, because all the balance factor will be simply 0, 0 as it is. Okay, and here also balance factor is 0. So everything is fine. Now in this left subtree, because you have deleted 18, so then also no problem is happening here. Okay, so this is there. Now next, if we delete 16 means this one. 16 means this one. If you delete this node, if you delete 16, then what will happen? If you delete 16, then 16 has one child. So if algorithm says that if it is having one child, then also deletion is not an issue. So you just simply delete it. Okay, 16. So once we delete 16 means this node, then because 16 has one child, so one child deletion is it is not a problem. Just its child will occupy its location. So you see here 10 has gone up, and 16 is deleted here in this figure. 10 has gone up and it has occupied the 16 positions. But the thing is that once you delete that, you have to check the balancing factor. Okay, so balancing factor for 30 will be 1, 2, root node 2 minus 1, 2, 3, which is minus 1. So minus 1 is within our range. So because our balancing factor should be either minus 1, 0 or 1, these three. So here once we delete 16, so you can see that this 10 will occupy the 16 locations, and this is fine. So what about the balancing factor of this node balancing factor is 1 minus 1 2, which is again minus 1, and this node balancing factor is minus 1 because 0, this side is 0 0 minus 1, this node balancing factor is 0. So you can see that this is balancing factor is 0. So this is fine. Okay, so now once you delete this, also you have to find that whether after deletion whether balancing factor is maintained. So all balance factor is maintained, so this is fine, we are fine with it. Okay, now yeah, now so we have deleted 18, we have deleted 16. Now we are going to delete this one 20. So 20 is this one, this node we are going to delete. Now 20 has 2 child, so once it has 2 child, so you have to little bit careful. Then what will happen once you delete 2 child? So 2 child, yeah, 2 children you can call it. 2 children means either this, who will occupy once you delete this? First of all, who will occupy this? It is as simple as like BST only. Either in order predecessor or in order successor will occupy this 20th location. The 20 node position will be occupied by either its in order predecessor or in order successor. So in order predecessor means in the left subtree the highest element, maximum element in the left subtree. Okay, and in order successor means the lowest element, the minimum element in the right subtree. So this you have to remember. In order predecessor means in the left subtree the maximum element. In order successor means in the right subtree minimum element. So whichever you want, you have to follow it, and you have to follow across the calculations. So here let's say in order predecessor is going to occupy this. So once you delete 20, so this 10 will come, which is in order predecessor. So what do you see? We saw that when there is a leaf node, then there is no problem. When there is a one child, then also no problem. When there is a two children, then you have to be careful. 2 children. So in that case, either in order. So now we are going to delete here. Once you delete this 20, so it's in order predecessor. In order predecessor means the maximum element from the left subtree will occupy that. So 10 will occupy this location, 20. So 10 has come, and its balance factor has been -2 because it is this side is 0 minus 1 2 minus 2. Now because its balance factor has been this thing. Yeah. Yeah. So in this case the balance factor, so one child. So first of all it is leaf node, then hey শয়তান দাঁড়া তোকে আমি কি করি দেখ পাজি। So 2 children. So now the balance factor here will be in this case -2. So balance factor of this 10 is -2. So what you have to do, you are required. So basically it will be like this. So this will become 25, and this will become 25. This will become 10. This will become 10, and this will become this 26. 26 will come here. So this won't be there. Okay. So this is how this left rotation will happen. Left side, left rotations. Left rotations will happen. Okay. Now this is how you can delete the node. Next node you have to delete is 35. So 35, if you delete this 35, so either you have to see in order predecessor or in order successor. In order predecessor is nothing but this node, which is 32. So 32, if you delete this, so this node will occupy 32, and then remaining things will remain same. Okay. After deletion of this earlier node, what is the balance factor? Now balance factor for 25 is 0. Balance factor for 1 2 2 minus 1 2 3 minus 1 for the root node. Now if you delete this, then this will come, and then the balance factor will be minus 1 for this 32, 0 minus, because yeah, and then balance factor for this is 1 2 2 minus 1 2 2 minus 2 0. So like that you can delete many as many element you want from the AVL tree. Only you have to be careful about the two children, because two children means you have to either find in order predecessor. In this case, every time we have taken in order predecessor, or you can take in order successor. In order predecessor means the left child who is the maximum left child tree, and in order predecessor successor means in the right child tree or the right sub tree, which element has a maximum minimum value, that will replace the deleted numbers. Okay, so this is how you should delete elements from the AVL tree. I hope you understood.